Hey, how you all doing? Welcome to another version of the embedded hour. And I think today we've got quite a good session coming up to today. We're gonna talk a little bit about space systems, and my friend Barry is going to come along and talk about one of his projects he's been working on, the flying laptop. We've got quite a packed session actually, so I'm just going to run through what we're getting. So obviously, welcome to everybody that's coming. If this is the first one, then welcome very much. Obviously, feel free to ask questions and discuss and communicate with us as we go through this. It's all a nice open environment that we want to have to discuss embedded systems and their use and such like. And if you'd like to come along and talk at a future one about your projects or what you're working on, then please do. That'll be really great. So everybody's welcome here today. We don't really mind whether you're a professional engineer, been doing it 20 years, or whether you're a university student or a maker or something. We want to have a nice open discussion, nice welcoming environment for everybody. We're going to record this. So I've set the recorder going, so we're going to record this and we'll make it available on YouTube after the event. And we've also got a little survey that'll pop around after the event as well. So if you could just take a few minutes to fill that out, it'll be really appreciated, just so as we can help us improve what we've got coming up. So today's one's slightly different actually, because we thought, like the last few, we've talked a lot about FPGAs and a lot about the different flavors of FPGAs. So how you could reuse FPGAs if they were from scrap and repurposing them, how we could sort of use Pink and little embedded systems. So we thought we'd be a little bit ambitious with this one. We thought we'd talk about space and space projects. Obviously, it's very relevant with the news of the recent SpaceX launch. I'm sure everybody was watching that with bated breath. I was so excited on the Wednesday, waiting for it to go, only to have to then wait a few more days for the launch on the Saturday. But it went up. It was really amazing, and it's good to see. It's good to see that challenge and that moving forwards. So I'm going to give you a little bit of an overview. I think most people actually are familiar with me from the work I've done around the MicroZ Chronicles and FPGAs. What you might not know actually is I've got quite a history in the space industry and developing for space. Actually, not a huge amount. Not all of that was always just designing FPGAs. Quite a lot of that was at more senior level, sort of chief engineer and so on. So a very system level sort of view. So I'm gonna talk a little bit about my space experience, some of my projects, and we're going to talk about some of the challenges that you'll find in space and space systems. And then I'm going to hand you across to my really good friend Barry. I've been working with Barry for about the last 18 months now. It's been really exciting. It's really rare actually that you meet an engineer that you can work with and just work with so well as Barry and I do. We seem to work together really well and make a great team. So Barry's going to talk to you today about a previous project he was involved in, which is quite interesting, which is called the flying laptop. So I think that'll be quite I'm really looking forward to Barry's talk on that. Previously, it's been a bit of a busy month for me since the last one. In fact, it's been a busy day actually. My day started at 4 a.m. with a webinar for some people in Japan in the Japanese Standard Time. So it's been a long day today. But I thought I'll get started, and I'll tell you a little bit about my background and my experience in space design. And actually, it's really interesting. Actually, it was working in space and actually working for Astrid when I was working for what is now Airbus, that actually got me started on this entire journey to writing about such things like the Zinc and creating blogs and creating content and sharing my knowledge. Actually, because one day I was sat outside a clean room at Astrid in Stevenage, actually, waiting for some testing to go on. We spent a lot of time down there. I was a little bit bored, so actually I sat down and I wrote a paper on how to design mission critical FPGAs. The picture of it's there. It ran in the Excel journal. I couldn't think of anywhere else that might publish it, because it wasn't an academic paper. It was more of a this is how to do it paper. So I sent it into Excel Journal, and they liked it, they ran with it, and then things just kind of went from there to me sort of creating now the Chronicle. So it was my working space and my love for trying to share that information that led to us all sat here today on a Friday afternoon having a chat about space systems. And the first project I actually worked on was a really interesting one. So my background was predominantly the defense side of things before moving into space. And I got started working as essentially as one of the design engineers. So my job on AlphaSat, which was part of the Inmarsat constellation, was actually to design a PCB board in there. We actually designed what they call the control processor module. And a control processor module, it had a couple of RTAX FPGAs on it. It had all the telemetry, in-band telemetry, and the telemetry control. So it was a really good introduction for me as an embedded systems designer designing for space, because this control processor module controlled the entirety of this nice black box that's there. Because I mean, the interesting thing that runs throughout my career as an engineer is everything I've designed has been a black box. It just seems to kind of run that way. So I was designing this control processor module. The interesting thing about this is the CPM had to actually control obviously the entirety of the module. So it had to control the analog inputs, the digital outputs, the digital beamforming ASICs on the bottom. It had to be able to switch in and out, redundant paths, and just really control the processor itself. And that, for me as an engineer, was really good, because although I've been working in the defense industry previously, I'd worked on, submarine systems and so on. It was really working on that project where I actually got to know a lot of the ultra high reliability processes and procedures that you need to use to make sure that if there's a prime and a redundant side, the redundant side, if the prime side fails, it can't affect the redundant side. If the redundant side fails, it can't affect the prime side. So that was a really eye-opening project for me in how it works. It was also eye-opening in the amount of documentation that you went on then to create as an engineer. So I'll be talking about it later on, but you're working through things such as the part stress analysis, worst case analysis, radiation analysis, and we even went and designed it was very different as an embedded system, because it's got to survive, it's got to work, it's got to survive launch. So one of the things that we would do actually is we would create an entire structural, I've never seen this used in any other area, but we would create structural models. So we would actually build circuit cards with nothing but daisy chain devices on them, resistors to mimic thermal loads, and we would build replica life-size models of this with the daisy chains on there and the resistors for heat. We would then take these into thermal chambers, into vacuum chambers, put them on shaker tables, and see how the design actually behaved when it was subjected to the levels of qualification and acceptance that it was going to be. In most cases, it worked. In some cases, we had some quite interesting definitions and some quite interesting failures. But that obviously is better. It's better for the issues and the failures to happen while you're on the ground than it is obviously while they're up in orbit. So that was my first sort of introduction to the space industry, was working on that embedded system. And by the time I left, by the time that project was completed, actually I was working as what at Astrium they would call one of the responsible engineers on the project. So I was responsible for the overall one of the overall processes. So working the overall design through all the qualification and system level acceptance that came off, working with the customer to get that through. My wife always thought it was funny, because I'd say sort of, I'm the responsible engineer, and she'd say, well, that means that most other engineers are irresponsible, which obviously, if you've ever met any engineers, then that's obviously not the case. Around that time as well, while I was working on, so we worked on AlphaSat, which was really great because it was like this big, it was a big expensive satellite, lots of design work gone into it, a big design team, some of the best engineers I've ever worked with worked on that project. And then along one lunchtime came the ability to, somebody asked me if I'd got any ideas for a CubeSat. So CubeSat's obviously 10 centimeters by 10 centimeters by 10 centimeters. And we sat around for a bit and we thought, yeah, we've actually got an idea. One of the things that we did at Astrium was really secure communications. So it's really important to have a secure link between your ground station and your satellite. You obviously don't want anybody to be able to seize control over it and control your satellite. And of course, the data that's coming down, the data that's coming down from these satellites, if it's an imaging satellite, is worth an absolute fortune. That data is that downstream data is worth an awful lot to companies. So companies start wanting to secure their networks and secure their systems. So we took a look at a patent that actually we had, which was to use one of the key things in cryptography is using really truly random numbers, not pseudo random numbers like your computer might come up with really true random numbers. So we decided that we had a patent on it, and we decided that we could use radiation. So the radiation effects, so single event effects, would strike an SRAM device, and those bit flips, we could use those bit flips because they were really random due to the fact that radiation is random, to actually generate true random numbers and then create these true random numbers and use this as part of the experiment. So this is exactly what we did. We proposed this into the UK Space Agency, and we created here which was called the UCube program. So we have I think if I can annotate this in the middle somewhere, annotate. So we created this application here, this little payload here, which was at the time, I think it was probably one of the most expensive CubeSat boards developed, because we actually dug around the lab while everybody else was using cheap commercial components that could fly. We actually dug around the lab and found some, dug around the stores in Astrium, found an RTX FPGA that we could repurpose for retask to the UCube. But importantly as well, we had a real interest at the time in being able to fly Xilinx FPGAs in space. So we wanted to fly RTX FPGAs. They're obviously they're anti-fuse FPGAs, so you can only program them once. If you get it wrong, you have to desolder them, and there comes with risk. The Xilinx FPGAs, obviously, they're reprogrammable, and we wanted to. At the time, this was before the RTG4 was available, so the Pro ASIC FreeRT was just not really suitable for this, and we wanted to get some experience in flying Xilinx FPGAs in space. So we actually talked to Xilinx, and they very, very, very kindly, because this was a CubeSat mission, they actually gave us one of their Vertex 4 space grade Vertex 4 FPGAs, an SX55, and we actually flew that as well you can't actually see it, but on the flip side of this, on the opposite side of this board, where there's the RTX FPGA on the top, on the bottom side of that board, there's a Xilinx Vertex 4 SX55. And we just went SEU hunting with that. So we went to characterize we characterized the performance of the FPGA on the ground in radiation on what we thought the tool would be. So we simulated it all, worked out how we thought the SRAM-based FPGA would behave in orbit, or in the orbit that we were going to see. And then actually we went away and created a design in the RTX and the Xilinx FPGA, the two talked together, that we could monitor that. We could monitor that in orbit and actually work out the performance, and then map that performance that we saw in the orbit back with what we predicted on the ground to help us understand a little bit more about that performance and that behavior. Obviously, one of the agreements for doing that with Xilinx was that we shared the data with them that we obtained. But that was a really great little project. And actually, we did that because we had no funding. It's like every company, you work on a timescale, on budgets. We had no funding to do that. We could find the parts. We could get people to lay out boards for us in the company and so on, and do the manufacturing. But as we didn't have any funding, so actually we did that on our lunchtime projects. And it was really quite nice. A few years later, I had one of the guys working for me who worked on another one of the projects on the UCube payload. And what was really quite cool, what I didn't realize till the end of the project actually, is everybody's name who worked on UCube was actually etched on the satellite, and it is now flying around in orbit. So I thought that was quite a nice little touch actually for the application and for the project. I thought I would have cleared the annotation. I thought that would have clear all drawings. thought that was great. So then after that, I spent some time doing some really, like I say, some secure TMTC, and that's really quite interesting, doing secure TMTC. You know, we worked into a lot of areas then, so we were doing sort of tempest design and a lot of high-grade crypto design, which obviously for a lot of reasons I'm not going to go too much into today, but a real lot of good, exciting design at not only the challenges of meeting the design for will it survive the rigors of space, but is that design secure and safe, and the data that's within it secure and safe while it's going through the ground, while it's going through ground testing and qualification, and then its launch and into space. And then finally, I wrapped up my on the tools bit of FPGA design and board design in space for a couple of years by being the chief architect for the 5th generation of telecoms processors. That evolved into into what became OneWeb, which has just had some launches and some issues. But what you can see, you probably can't see it too well, but what you can see under the middle here is that's a Vertex 5 FPGA, a Vertex 5 QV FPGA, so Vertex 5 space grade FPGA. And again, you get these nice projects as you work through them. And then I left Upstream and actually became the chief engineer at E2V. So you might not have heard of E2V, but you will probably have heard of some of their products. So they're actually based about 20 miles away from me in a town called Chelmsford, and they make CCDs, so charge coupled devices for imaging, particularly for space. So the Pluto Flypast New Horizons, they did the images for that. The Rosetta lander, they did the images for that. In fact, actually, there's a really good chance if you've seen an image from space that it was made by CCD, made by the team in Chelmsford, and that also includes the Hubble Space Telescope. So the Hubble Space Telescope uses E2V CCDs as well. And I was working on, and I inherited when I started working at E2V as a chief engineer. I inherited the replacement project for what is potentially one of the Hubble's replacement in the ultraviolet field. So when Hubble retires, there's no ultraviolet astronomy. It's very difficult, thanks to the ozone layer, to actually do that from the ground. So you need to be in orbit. So we were working with a really multinational team to pull this off. So we were doing it at E2V. We were doing the images, but we were actually doing not only the sensors, but this time we were doing the full imaging system, the full camera system. So the enclosures, the cooling systems, to cool the thermocouple, to cool the CCDs down, and also the electronics. And working with the team, actually the electronics went to RAL. And they were done. But you can see there on that picture there, there's a nice little example of what you can see, the difference you can see if you look at a picture using visible wavelength, or if you look at it using ultraviolet. So you can see using that ultraviolet imaging actually gives us a little bit more understanding and helps us understand a little bit more about our environment and about the world and the universe actually that we have. And that's one of the great things. Actually, I write a lot. I bore you all lots with things about sort of embedded imaging and embedded processing. But one of the great things about embedded processing is actually we can use these devices, CCDs, thermal cameras, and such like, to actually give us vision outside what is visible to us humans. So we can see in the X-rays, in the thermal, in the ultraviolet domains. It extends our capabilities and our understanding. So we can go there and do that. So I'm still, obviously I left E2V a few years ago, and I'm still very much involved in the space industry, in working with space. So now I run my own company, my own consultancy, Aduvio Engineering, and we have and at the moment I have a couple of projects ongoing. One for the European Space Agency to look at the existing IP cores that the European Space Agency has, and to determine the quality of those, and work out whether there are any issues with that, and what we would like to do going forwards. And I'm also, like I said, I'm also working with Barry actually on I'm also working with Barry on a project called Plato, So on Plato, we're designing a number of boards and a number of FPGAs to actually control some temperature. I don't want to say too much about it because it's not my. There's another company involved that we're contracted to, but it's a really exciting project and really exciting program. So all these things have got some interesting things that I've learned over the years and that are interesting now, and I think Barry's going to talk about them more as we come to talk about his session in a couple of minutes. But some of the challenges that you see when you develop an embedded systems for space. In fact, one of the great questions you can ask anybody at interview is you can ask them about what's the biggest challenge you'll find if you're working for space design and space environment. And you can always bet your life that they're going to say, well, it's cold, so it's keeping the systems from stopping the systems from freezing. Actually, it's completely the other way. What we want to do, and what the challenge is actually, is in keeping these components actually cool, and particularly cool to the derated temperature rules. So to get the maximum reliability for components, we don't want to run the components at 80 degrees C that they might be rated to, or 140 or 150 degrees C that they might be rated to. We want to derate that a little bit, such that they're not under as much electrical and thermal stresses. And you'll spend a lot of time doing what I call part stress analysis. I've spent the last few months doing part stress analysis for three boards on a project. So you spend a lot of time doing this part stress analysis and trying to make sure that the derated temperature is just it. So to give you an example, if you take a look at the Xilinx Vertex 5 that I mentioned, that's rated to 150 degrees C for its junction temperature. But the European Space Agency rules say that actually the junction temperature can be no more than 40 degrees C below that. So that brings you to 110 degrees C. Which, when you've got a device that is as capable as that and can draw, it's capable of drawing a significant amount of power, it's a real challenge to be able to keep that derated temperature. So you need to have really clever, really smart sort of active cooling systems in there to try and pull it away. Obviously, you can't use a fan because there's no atmosphere, so you're limited very much to conduction, really, to pull away the heat to base plates. But then you have to take into account all the base plate temperatures as you're doing it. We have some interesting issues regarding shock and vibration, and they're really interesting because not only do we have to worry about the devices staying on the board, but we have to worry about other aspects as well. So perhaps one of the more interesting projects I saw was some equipment that was on a shaker table at Astrium. It was payload equipment, so it had to be turned on while it was during launch. And that was a bit of a problem because on the shaker table, after a while, it would shake for a while, and then it would stop, and the device would just stop working. So we had to have a little bit of an issue as to why. And you go away and investigate this, and actually, it turns out that some contacts within the FPGA are actually shorting out, and that the FPGA has been designed as a one-hot state machine, and it's not being designed with any high reliability rules in place. And as such, it jumps into one of the 110,000 illegal states that it had due to this rather large one-hot state machine, and the machine locked up. So even while we think about as FPGA engineers or as embedded system designers, what the impact of, you might think that shock and vibration really only has an impact upon whether the devices actually physically stay connected to the board or whether they break on the board or not. That's not necessarily always the case, and there are areas where we still need to consider that and make sure that we've got the best applications from it. Now, one of the members has just actually popped up a comment about the Kintex Ultra Scale, which Xilinx have just released. Now, I'm not sure if that's actually being used in any satellites or not yet, but it looks a phenomenal device. Actually, it looks really like it's the right device at the right time for a lot of space applications. And I guess a lot obviously that's going to come with certification too. I guess it'll be QMLV or the non-hermetic version of that, which I can't remember off the top of my head. And obviously the final point, obviously, you've got to think about the radiation side of things. So everybody always thinks about the the traditional bit flip, the input, the register turning from one bit to another. That's fun and that's interesting, and you can analyze that and design for that. But what's you have to consider more is the more destructive components, the single event latch up, the gate ruptures, and you have to as well have to actually consider the total ionizing dose, which actually that makes our system slow down. So as the devices gets more radiation, what happens, sees more total ionizing radiation, what happens is two things happen generally. The power dissipation goes up and the timing performance slows down. So when you do the timing closure and place en route, you have to make sure that you've included and mitigated for this timing closure at the end. Just move on to the next slide. So if you've never seen any single event effects, there's a couple of pictures of what you can see. So if you've got a simple thing like a standard clock, and it gets hit by a single event, or you see a single event, then you can see things such as you get missing pulses. It might just go to one level and stop, or you might begin to see additional clock edges, or a combination of different transients. So you need to be able to design your system to mitigate around these events occurring. They might hit a linear regulator and provide a glitch on a linear regulator, which needs to be filled out. They might flip your state machine into an illegal state, which means you need to design your state machine to mitigate that back. So all these skills are really like the domain of the space expert. And actually, I'm thinking that I might put on a 1 day or a half day sort of design for high reliability course, if anybody's interested, that we can do while the lockdown is on. So the last thing I'm going to say before I hand over to Barry, and Barry tells you all about his excellent flying laptop project, is one of the other things that I've learned as I've gone through this and been working in the space environment is we have a lot of process as well. So you'll find that process becomes very key, because it's only by following a sensible engineering process that you can be sure that there is the maturity in the project, and that there has been the due diligence on the project, that it is safe to move on from one stage to the next. So it's really important to do that, and to have those gating milestones. It might not seem like it's the most fun all the time when you have to create documents or you have to spend days attending these, but it is really well worth the time and effort. So our component choice as well. So everybody always thinks that space is really on the cutting edge of technology, and actually it's archaic. So occasionally you'll get the really exciting announcements like the Kintex Ultra, but actually a lot of space grade components, because of the qualification and the certification that goes into them, there's such a long lead time to get things into this, then it takes time. So you're generally designing with slightly older technology than what is available off the shelf. And you've also generally got some really, really long lead times. So, 12 or 18 months is not an unusual lead time for components, particularly even like not just FPGAs, but maybe or processors or memories, but even things like diodes and resistors and capacitors can be on the same sort of lead time. So it really leads you to focus a lot more on your engineering effort up front to make sure that you're not doing bomb changes all the time, and that you actually really do need what you want, because there will become a hard date that you have to sign off by to actually ensure that you can manufacture everything and meet the rest of it. Now, of course, actually you can look at a commercial component, and you can do upscreening of commercial components, and that's generally done if you want the performance. It's never really done if you want the cost saving, because it's not going to really save you it's not really going to save you anything, because you're still going to go through a lot of tests. You're going to go through testing and certification to make sure that those are working. And what you're going to have to do is you're going to have to buy a lot of components, not a lot as in quantity, but actually a physical lot of the components as they come off the production line. So an actual serialized lot that's fully traceable, and you're going to buy that one lot, and that's the lot that you're going to qualify for use in space. The next lot that comes off the next day, that's no good. That can't be used because you've only qualified that lot that was certified on that particular day. So it is done, and I think you'll find a lot of people do it. I mean, obviously in the CubeSat environment, the small sat environment, they're not too worried about it. But in the small sat, the medium sat, and the large sat sort of stuff, this is really important that it's done. And then finally, we're going to run through all the design analysis that there's going to be a lot of detailed design analysis that you're going to do, and you're going to spend a lot of time really testing out your mathematical skills and your design analysis skills. Now I've been rambling on for much longer than I actually intended to, so I'll be getting told off again. So I'm really going to pass you over now to Barry, who's going to talk about his flying laptop, which is I think is a really quite a good project. So I'm going to stop sharing my screen, and Barry will start sharing his, hopefully. So Barry, if you're still there, over to you, sir.
Hi, Adam. Thanks very much, and good afternoon, everyone. Or whatever time of day it is for you. It's the end of the week here in England. It'll be weekend coming soon. Great to be here, and Adam, thanks very much for those words of introduction. I agree. It's great to be working with someone you get on easily with. It really does make the project fly. One day we'll talk about Plato and what we've been doing on it. It's slightly different from the flying laptop. It's great fun. So I'm going to try and share my screen now and run through a slide set with you. Host needs to enable me to do that, please, Adam.
Oh, that's something we forgot to do on the setup. Up sharing. All panelists. There you go. Now you should be able to do that now.
Okay, thank you. Let's pick the right one. Here we go.
There we go.
Lovely. Right. So, the flying laptop. Spoiler alert, it isn't actually the thing you put on your lap and play computers with, but we'll come on to that. It is a big embedded system, and it's one I was working on for some time. My background, by the way, I've always been a techie. I drifted into being an academic and then moved out and became an industrialist. First project was a home networking system, a home entertainment networking system, but it turned into space-related test equipment, which has gradually morphed into bits that go on satellites and other things. I'm doing some analog electronics for electric cars at the moment. I've got one or two other little technical projects, and just for fun on the side, I also am part of the production team for a 3-day rock festival, although we sadly had to postpone this year's. Right, the flying laptop. Here's what I'm going through. There's some acknowledgements. I've got a debt to some of the people involved. Bit of an introduction, a look at what's in it, a picture from the Middle East. Look at the content in a bit more detail, and then design considerations. I'll try not to overlap Adam too much in the process of that. The person we really very much have to thank for the flying laptop is Jens Eichhoff, who works for what is now Airbus, who is a visiting professor at the University of Stuttgart and ran a project there for the students, and he's provided a lot of the pictures and information. Some of it's from a paper that we gave listed here, and the group of people at the bottom there were those involved at the time. It's a long project. It's well over 10 years start till now, so there's a huge number of other people, students and staff that are also involved. So that's it's not a small project. Space is big and broad. The purpose I mentioned was a student project, really, to give students some idea of what it takes to design and operate satellites. You can talk in theory, that's all very well, but there's nothing like actually doing it for real to find all the issues and problems and the things you don't normally talk about. The satellite itself had a major purpose of validating the onboard computer system with a view to selling that computer system on to other missions. That has happened. It's been successful. The set up the computer system is now built into other European projects, so that's going forward nicely. But for the student purposes, it was looking at imaging. Images always look great, and imaging is one thing that space provides for you, which is really useful. Multispectral imaging for various projects. I'll mention that again in a moment. A little bit of subverting what's on the satellite to detect near-Earth objects, not what the equipment was designed for, but just to see if it's possible. Observing ship traffic and comparing optical and AIS data. AIS is a data system that ships of any size are required to enable which transmits information about what they are, where they're going. And if you see a ship that should be transmitting the data and isn't, you can infer that something is wrong. Either they're in trouble and need help, or maybe they're pirates and shouldn't be doing what they're doing. In either case, there's a good reason to go and find out, go and give them a visit. And finally, an experimental laser system, communications backwards and forwards via laser, potentially giving you much more bandwidth. So the question was, could the satellite support a laser system which needed fairly accurate pointing? And it turns out that they could. 2 years into the project, with a revised stabilization algorithm, they were able to transmit data up and down with a laser fixed to the body of the spacecraft. So the whole craft itself was stable enough to do the job. Context, major parameters for this satellite. It's in a low Earth orbit, 600 kilometers above the ground. It's what's known as a sun-synchronous orbit. It passes over different parts of the world on each orbit, but whenever it passes over the same point on the Earth, it does so at the same time of day. So the shadows are the same. It's useful for comparing pictures from one pass to another. It's a very common orbit. 600 kilometers is not particularly high when you compare it to GPS at 20,000, or geostationary communication satellites at 36,000, or the moon out there at 384,000, or indeed the Plato project that Adam and I are working on at the moment, which is 1,500,000 kilometers, 4 times as far as the moon. So my work is gradually moving away from the Earth. In order to stay in orbit, the thing is whizzing around at 7.6 kilometers per second, 17,000 miles an hour. As you go further out, you don't need to travel quite so fast. So GPS is a bit slower, geostationary slower still. The moon's only traveling at 1 kilometer per second. It's fairly lazy stuff. But the orbital period of flying laptop, 1.5 hours roughly, just a little bit more. Its size, 60 by 70 by 80 centimeters, think large dishwasher. So not something you put on your knee, but something rather bigger. It has deployable solar panels and the mass 120 kilograms. It makes it technically a small satellite, not a CubeSat. Those are really tiny by comparison. This is what's historically known as small. As technology is advancing, satellites are getting smaller and lighter. And that's great because it means the launch cost is coming down. There's a whole new era coming where it's very easy and very cheap to put satellites up. Right, so what's in it? I've mentioned some of this. The cameras, there's a panoramic camera, relatively wide angle monochrome camera, and then 3 narrower cameras in the near infrared, red and green parts of the spectrum. You don't get natural images, but by combining these 3, you can actually infer the type of vegetation you're seeing, and indeed the health of the vegetation. So this is great for seeing what's going on. Are there any crop failures? What's doing well? What isn't? The AIS receiver for the marine traffic, a reference there if you want to look it up, and that laser comms experiment, which is just a tiny part of what's in the box. The rest of it's there to support those experiments. And we find, of course, a power supply, solar cells, 192 watts maximum output when the sun is shining directly on them. Of course, as the satellite goes around the Earth, that's reduced. Indeed, it's in darkness for half the time. So energy storage with well tried and tested lithium iron phosphate batteries. Power consumption has to be kept quite modest in order to make sure this is enough. This has to feed not only the payload but a load of instruments. We need to know where the satellite is. We use GPS receivers, 600 kilometers compared to 20,000. Well, it's just sitting on a large hill, really. So GPS works fine on satellites as well as on the ground. You just have to make sure your receivers can cope with 17 kilometers, 6 kilometers a second, 17,000 miles an hour, which is a little bit more than we're normally used to. There are some sensors to assist in pointing. These really are just photocells looking for bright source of light in the sky. and star trackers, a little bit more sophisticated cameras to take a picture of the heavens, compare that with a database and infer where the satellite is and which way it's pointing. And here's one of the little side experiments. Can we use a star tracker that's taken a picture of the sky to actually spot near Earth objects that might not normally show up until you get close to them? Haven't heard any results from that experiment yet. But not only do you want to know where you are, you want to know where you're going. So there are gyroscopes, fiber optic gyroscopes. Mechanical moving things are tricky, as I'll mention very briefly later. So fiber optic is a solid state used in aircraft, so it's well tested. Magnetometers, we can use the Earth's magnetic field to give us an indication of where we are and which direction we're pointing in. We certainly need to change the orientation of the spacecraft to point the cameras at the right places. And you might think fairly obviously that's rocket engines, but that's not the only solution. And rocket engines come with all sorts of handling problems for the fuel. It's quite nasty stuff. And indeed, the lifetime of a satellite is typically determined by running out of fuel. So alternatives that don't run out are quite attractive, and they're a lot safer. Flying Laptop uses 2 reaction wheels. That's just a flywheel on a motor. If you change the rotational speed of the wheel, you get a reverse force which can actually rotate the satellite. And magnetic torquers, electromagnets that interact with the Earth's field and generate a torque. And there are certain characteristics of reaction wheels that in combination with magnetic torquers become a nice combination. I won't go into that here. That's not really an embedded system issue, but a nice bit of technology nonetheless. And of course, there's communication system. Not much point throwing this thing up if you can't tell it what to do or get data back. 2 distinct systems. The data downlink, 10 megabits per second. That's really quite a low data rate. You really want to be talking gigabits per second for high resolution cameras, but that's a manageable link. And then there's the command and control, which is kept separate, both up and down. Here's the real thing. I'll give you a very quick tour of what's on it. This thing on the side is a solar panel. The front side is the active side. There's 1, 2, and a third one. They get launched folded down. There are hinges here and latching mechanisms on the edge. So these are folded back for launch, and when it leaves the launch vehicle, the latching mechanism operates and the panel folds out rather like a laptop opening up. It's a sort of mixed derivation of the term. The technical designation of this was a future low Earth orbit platform, the experimental proving the computer system aspect of it, but future low Earth orbit platform is FLP, and FLP in someone's eyes rapidly became flying laptop, hence the term. So apart from the solar panels, we have a GPS receiver on the front. At the top here, 2 separately pointing star trackers. There are some solar cells around the top for tracking the sun. But then inside, here are the 3 main cameras. They've got covers on at the moment. Those will come off close to launch. The panoramic camera is this black, rather smaller device here. And next to it, the laser communications experiment, transmit and receive. Underneath the main radio antenna, we're in the microwave band, and we're using circular polarization because that's convenient for satellites. You can't be sure which way up they are normally as they orbit. So traditional earthbound horizontal and vertical just doesn't do it. And then tucked away inside, everything is crammed in, the main computing and control unit at the bottom, batteries to the side, various other instruments tucked away here, not I'm sorry, visible. And a little panel of connectors for just joining it up on the ground, making sure it maintains charge in the batteries, checking the state of health of everything, and that unplugs for launch. At the bottom here, there's a ring which is used for attaching to the spacecraft, to the rocket that's sending it up. There's just a spring underneath to push it out. Nothing clever, nothing elaborate. Keep it simple is very much the mantra for space. If you make it complex, there's too much to go wrong. It left Earth just under 3 years ago now from Baikonur in Kazakhstan on top of a rocket with some 70 or 80, I forget the exact number, other satellites. You rarely launch one satellite on a rocket, that's just too expensive. The primary mission for this was an Earth observation satellite, which was very large, but then there were several dozen smaller satellites in varying sizes, right down to CubeSats, which got launched at the same time. So making the best use we can, and you see it's a relatively clean launch, none of this smoke that we get from the space shuttle. Right, I'm going to take you inside now for a little look. If you can see the detail here, that's great. If not, I'm just going to point out that the major features here. The cameras, panoramic camera here on the left and the spectral cameras next to it, the laser experiment on the top right, payload along with its controller. Now that little bit is the purpose of the satellite. The rest is infrastructure to make sure it operates. You can probably, well, you can certainly see here fairly easily, you've got two bits that look much the same. If you can see the detail, there's an N and an R tagged on to the name. That's nominal and redundant. So there's a nominal unit which is operational, unless it fails, in which case a redundant unit can be switched in to take over. So we improve reliability by having spares. Right, the infrastructure. Let's go back over to the right. Top here, data downlink, radio transmitter, and another copy, the spare. Command and control, 2 receivers and 2 transmitters with a spare. Deployment mechanism for the solar panels, again with spares. Further down, battery strings. We've actually got several strings of battery, but 3 major lumps. They feed down to the bottom into the onboard power bus, which combines them as they're available and then feeds them out to all the various units with switches so that you can turn them on and off. Any failed unit gets disconnected. Then down here, you sort of go in clockwise. Bottom left is a load of heaters to make sure things don't get too cold. That's before they're operational. Once they're operational, they generate plenty of heat to keep hot, and then, as Adam mentioned, you have the problem of keeping them cold. But during launch and until you've checked systems out, you need to make sure they don't get too cold to be switched on. Next here, GPS receivers, 3 receivers, 3 antennas, and multiple local oscillators. Fiber optic gyroscope. You need 3, X, Y, and Z, but you put 4 in, so that a failure of any one leaves you 3 working devices, and they're physically arranged so that any 3 out of 4 will do the job. Reaction wheels, again 4, we only need 3. Magnetorquers, X, Y, and Z, but they're doubled up, so there's 6 of those, 2 on each axis. The magnetometer, 2. The sun sensor, 8 nominal and 8 redundant, pointing in different directions. And then in the middle, as it were, the heart of the embedded system is the processor, based on a Leon 3, nominal redundant. Connected to that, the decoder and encoder for the communications. So that's separated out. We don't waste computer processor power doing that. It's best done outside in an FPGA. Again, nominal and redundant. And now we're in the bigger picture, you can see that the processor at the top connects to both of these encoders. The other processor also connects to both. Each encoder connects to both receivers and both transmitters. So any failure, you simply switch into an alternate path and you have a reliable route through. Between the processor and the rest of the satellite are these I/O boards. and that was my part of the game, to design this this I/O board to let the systems communicate. Again, two of them. Slightly different approach to redundancy on the two sides here. On the processor side, there's a link to each processor. On the peripheral side, the wires are actually simply joined in parallel across the two units, and we rely on buffers that go open circuit and stop driving the lines when we want to turn the board off, the I/O board off. One little thing that you may find slightly surprising, maybe not, from the receiver to the decoder to the power bus, there is a very short path, very short set of lines. This is the if all else fails, turn it off and turn it back on again route. Yes, we do it on satellites as well. Okay, the computer, as Adam mentioned, it's not really cutting edge stuff. If you look at this, it's a 33 megahertz processor, which for what it does is not at all bad. It's a Leon 3, it's rated part. It comes with a whole 4 megabytes of non-volatile RAM, sort of disk equivalent, 8 megabytes of static RAM for working memory. Not a lot, but enough. There are spacewire interfaces to the I/O board, and the encoder decoder. CCSDS is just a standard abbreviation, an abbreviation for a standard. There are bits and pieces that aren't too important, and it's an ITAR item. For those who know about it, that just means lots of paperwork. The operating system on that, though, may be of interest. It's RTEMS, the real-time executive for multiprocessor system. It's a long history through defense into space. It's an open source system, which lots of people have had eyes on it. It's relatively straightforward, single process with multiple threads. There's no memory management in order to make sure that timing is deterministic. It's very important to have accurate timing, more important than high throughput. So it's kept simple. POSIX API, and there are many ports. Spark Leon is the one used here, but you can find it all over the place. The I/O board, just to give you a quick look at it, is here on the left. It's FPGA based, Actel, now Microsemi Pro A63. Commercial part, not radiation tolerant. This was a cheap satellite, so we're using commercial parts. Nonetheless, although the mission lifetime was supposed to be 3 years, which we're coming up to, it's not been necessary to switch over to redundant systems yet. So actually the mission has been extended to another 3 years, so potentially 6 years. We'll see how it gets on in another couple of years' time, see if we can extend it further. So this commercial part is doing fine in space. The memory, the top here is volatile memory. There's another set of similar packages on the bottom of the board, and then all of the interfacing through buffer chips to isolate the peripherals from causing any problems back to any other peripheral. So we need to make sure these are isolated. If something goes wrong somewhere, it mustn't affect anything else. The I/O connections here, there's 100 pins on each of these connectors. They're micro miniature dense connectors. 2 spacewire ports here and a power input. This is an engineering model, not a flight model. These connections will fall apart, and this is just a test. The thing on the right is a prototype of the encoder decoder. That ended up on another copy of the same hardware. We managed to reuse the hardware, although we didn't actually put as many buffer chips on to do the encoder decoder and the I/O. So we managed to get a little bit of cost reduction that way. Let me remind you, the I/O interface is here. That board, 2 spacewire interfaces, 10 megabits per second, had actually more memory than the computer processor board. We had 4 meg for operational data, so we could store things like the latest position, the latest speed, direction, and so on. So should a processor fail, switching to the second processor could immediately pick up not too stale data and not need to go through a whole calibration process. 16 meg of data for experiments. Most peripherals were serial interface, 26 of those, one I-squared, a couple of I2Cs, and a few logic inputs and outputs. So I remind you, 3 GPS receivers, 4 oscillators, 4 gyroscopes, 4 reaction wheels, 6 magnetorquers, 2 magnetometers, 2 star trackers. Oh, no, there's a payload in there somewhere. It's sort of hidden in the detail. And of course the power controller. So design considerations. 4 main ones that are just worth mentioning. Vibration. This is a relatively slow launch, actually, an hour to 500 kilometers. The latest SpaceX was more like 10 minutes to 400. But you're going from nothing to 6 kilometers a second. You're going through the atmosphere at a high speed. You get a lot of buffeting. There's a lot of vibration caused by that. You're basically sitting on a blowtorch ramming its way through something quite difficult. Having left the main payload at 500 kilometers, it then pushed up another 100 in the next 90 minutes, so the 600 for all of the piggyback units. Quick example of what happens if you don't take this into account. Here's just an experiment on a shaker table that simulates a launch. This chip wasn't securely connected to the circuit board. You might think that something on the scale of fractions of a millimeter isn't going to be affected by vibration, but it surely is. Every single one of these legs has fractured at some point, some at the bottom, some at the top. It is an issue. Atmospheric conditions, there isn't any. We're in a vacuum. There's a mechanical problem. Moving parts are tricky. Lubrication is difficult. Most oils and greases boil off in vacuum, although we've got some solutions now, and we get vacuum welding, so moving parts stop moving. Air pockets and outgassing. When you build something on the ground, you've got normal atmospheric pressure. In a vacuum, that gas provides an outward force. In a big box, you drill some holes to make sure the air can escape in launch. If it's a chip package, you can't do that, and you may have a problem. And also plastics may seem hard on the ground, but they'll also boil in the vacuum, and that puts nasty deposits on lenses and things and is desperately unpopular. The solution for both of those is to encapsulate in an epoxy that adds strength and prevents the outgassing. Temperature control, as mentioned, without air you've got to rely on conduction and radiation. You can get very hot in sunlight, you get very cold towards absolute zero. If you've got enough thermal connectivity, you average out at something reasonable, which is of course what the Earth does, and you need to stay within this operating range throughout. I won't say any more. I've mentioned heaters. Sometimes you'll see spacecraft spinning to balance the heating and cooling, and you typically get a specialist team to do thermal design and management. Radiation, I'm conscious of the time here.
Yeah, I think we're really running out of time, actually. So if you could just sort of quickly wrap up, that'd be.
So let me whiz through these just to give you the headings then. Total dose, as has been mentioned, transient, latch up, signals you don't want. There are mitigating solutions, error correcting memory, triplicating the logic and voting on the output. Something, yeah, 500 upsets in RAM over 10 weeks, 50 a week, 7 events per day. It is real, and it's interestingly not evenly distributed. There's a bit of the Earth where you get more upsets than others. It's known as the South Atlantic anomaly, where the Earth's magnetic field dips and doesn't provide quite as much shielding as elsewhere. The magnetic field is beneficial, but it's also problematic in that it can induce voltages, so you may need to worry about signals. You have, as we did on the flying laptop, to put galvanic isolation, break signals, so you can't get these loops. Right, sorry about the rush there.
Not a problem.
Flying laptop here. G-Predict, if you're interested, nice program that gives you a graphical display of where satellites are at any time. British Interplanetary Society, more information, particularly forward-looking and more out of the blue type experiments in science, and questions if we have time. I think I should stop sharing and.
Okay, I can steal you. I can steal your screen.
Excellent, you do that.
And share my screen. So thank you for first thing, Barry. Obviously, thank you very much. That was fantastic. Really, actually, we've talked a lot generally over beers about the flying laptop, but it's the first time I've actually really understood a lot of it. Obviously, it's quite interesting to see. And again, you always have that dual redundant, that prime redundant stage, and when you've got several interfaces, obviously, it becomes quite a weight penalty actually that a lot of people don't consider. For when you've got all that cable in and those connectors in there. We have literally a couple of minutes left, so if anybody has any questions, please feel free to pop them in the chat window or raise your hand, and we'll try and ask them. And you can, if not, you can send me an email. So somebody's just asked actually, what's the starting point to get started as an embedded designer for space? And actually, the best way really is to try and get a job really with one of the primes. So like look at some of the companies such as Astrium, OHB, RAL Space. There's actually, I think you'll find there's quite a lot of companies about that do space design and design for space. I know particularly in the UK, actually, the space sector in the UK. Actually, we had a gentleman on the call today called Ray Stott. And he's a recruitment agent for does a lot of space recruitment agency through his company as well. So if you're looking for interest in space, take a look at what opportunities are out there via the large prime companies that are offering, some of the smaller companies. Talk to some of the specialist recruiters that are out there about what applications they might have, what roles they might have in the space field, and then we can move on to that. So Royce just asked if there state machines should be coded in different ways when designing for space FPGA applications, and I could spend an hour talking about FPGA, talking about state machine design for space, but actually generally yes. The main thing we need to consider is how the FPGA performs when it moves from how the state machine performs when it moves, if it gets a single event upset that moves it into an illegal state. So we need to be able to design our state machine such that it can either do one of two things: that it can either tolerate that and continue operating, or that it can detect that and gracefully correct and gracefully shut the system down, gracefully fail. In other words, like I mentioned earlier on, if anybody is interested, I will perhaps put on a session about some of the design techniques that we can use for designing in space that will cover sort of embedded systems, board level design, hardware design. Somebody else was just asking about the RFSoC and if the RFSoC is flying in space. I don't think it is because it's not qualified for space. I would imagine you will find a lot of RFSoCs though used in ground stations where you want to communicate with satellites and you want that performance and that agility. So I was saying, so are satellites not totally enclosed like a box in space, or is it designed that way? Actually, they're not entirely enclosed. So like as Barry was showing, generally they will have panels, and you will mount the equipment onto those panels. So the equipments will be designed to withstand the shake, rattle, and roll and the atmospheric venting, but they will be bolted onto the panel. But the panels themselves, the satellite themselves, will not necessarily be sealed, completely sealed, in enclosed units. Obviously, it depends upon what the satellite's actually doing, but that's not always the case that they are. We also have, I'm still alive. We also have a couple of other questions actually that have come through, saying, is it a realistic proposition to put a very small geometry chip into space, or would the upsets become unmanageable? So I'm not a radiation specialist. I can, like many engineers, I can talk about it and bluff my way through a lot of it. I think actually I've heard that the smaller nanometer chips, the sort of the 7 nanometer ones, actually behave slightly better due to the FinFET technology of them in radiation than what some of the larger nodes do. But I've not seen an awful lot of work done on that. And somebody else has said they'd love to hear a talk about radiation mitigation. Yeah, we can put on a talk about that and actually chat about sort of the different techniques that you can have. You know, the scrubbing of the configuration data, the readback, it's something really interesting things you can do with Xilinx technologies around the essential bits and critical bits, which tell you, you know, how many bits of your configuration bits are actually really essential for your design. So, Graham, if you're still listening, I will try and put something together. Maybe we'll have a special edition. The one last question. Somebody's just asked about any open source FPGA projects being used in space systems. I'm not familiar with any open source FPGAs being used, so I'm presuming you're talking about sort of the design tools that get used in there, such as Lattice. So I'm not too familiar that they will be used. I tend to think generally that you want tools of known good quality, so companies might shy away from using open source. But I stand to be corrected and probably will be now I've said this. Right, I'm gonna wrap this up now. I'm gonna thank you all for coming and spending your time with me. Hopefully we'll see you all at the next one, which is on the 10th of July. And what I'd really like, you know, if you've got any questions or comments, please reach out to me. If you'd like to come and talk at the next Embedded Hour, then please drop me an email. You know, we're open to everybody. We want to make it as open as anybody can be to just come and talk. And we want to talk about a wide range of diverse embedded systems topics. So with that, thank you very much, and I'll put the recording on YouTube and share it on social media and such like. But until next month, thank you very much, and take care.